I'd like you to ask yourselves, what do you feel when you hear the words organic chemistry? Like, what comes to mind? There is a course offered at nearly every university that is called organic chemistry. A flood of content that overwhelms students, and you have to ace it if you want to become a doctor or a dentist or a veterinarian. And that is why so many students perceive this science like this, as an obstacle in their path. And they fear it, and they hate it, and they call it a weed out course. What a cruel thing for a subject to do to young people. Weed them out. And this perception spread beyond college campuses long ago. There is a universal anxiety about these two words. I happen to love this science, and I think this position in which we have placed it is inexcusable. It's not good for science, and it's not good for society. And I don't think it has to be this way. And I don't mean that this class should be easier. It shouldn't. But your perception of these two words should not be defined by the experiences of pre-med students who frankly are going through a very anxious time of their lives. So I'm here today because I believe that a basic knowledge of organic chemistry is valuable, and I think that it can be made accessible to everybody. And I'd like to prove that to you today, if you'll let me. Here I have one of these overpriced EpiPens. Inside it is a drug called epinephrine. Epinephrine can restart the beat of my heart, or it could stop a life-threatening allergic reaction. An injection of this, right here, won't do it. It would be like turning the ignition switch of my body's fight or flight machinery. My heart rate, my blood pressure would go up, so blood could rush to my muscles. My pupils would dilate. I would feel a wave of strength. Epinephrine has been the difference between life and death for many people. This is like a little miracle that you can hold in your fingers. Here's the chemical structure of epinephrine. This is what organic chemistry looks like. Okay, it looks like lines and letters, no meaning to most people. Okay? I'd like to show you what I see when I look at that picture. I see a physical object that has depth and rotating parts, and it's moving. We call this a compound or a molecule, and it is 26 atoms that are stitched together by atomic bonds. The unique arrangement of these atoms gives epinephrine its identity. But nobody has ever actually seen one of these because they're very small. So we're going to call this an artistic impression, and I want to explain to you how small this is. In here, I have less than half a milligram of it dissolved in water. It's the mass of a grain of sand. The number of epinephrine molecules in here is 1 quintillion. That's 18 zeros. That number is hard to visualize. 7 billion of us on this planet. Maybe 400 billion stars in our galaxy. You're not even close. If you wanted to get in the right ballpark, you have to imagine every grain of sand on every beach under all the oceans and lakes, and then shrink them all so they fit in here. Epinephrine is so small, we will never see it. Not through any microscope, ever. But we know what it looks like, because it shows itself to some sophisticated machines with fancy names, like nuclear magnetic resonance spectrometers. So visible or not, we know this molecule very well. We know it is made of 4 different types of atoms: hydrogen, carbon, oxygen, and nitrogen. These are the colors we typically use for them. Everything in our universe is made of little spheres, and we call atoms. There's about 100 of these basic ingredients, and they're all made from 3 smaller particles: protons, neutrons, and electrons. We arrange these atoms into this familiar table. We give them each a name and a number, but life as we know it, it doesn't need all of these. Okay? Just a smaller subset, just these. And there are 4 atoms in particular that stand apart from the rest as the main building blocks of life, and they are the same ones that are found in epinephrine: hydrogen, carbon, nitrogen, and oxygen. Now, what I tell you next is the most important part. When these atoms connect to form molecules, they follow a set of rules. Hydrogen makes 1 bond, oxygen always makes 2, nitrogen makes 3, and carbon makes 4. That's it. H-O-N-C, 1, 2, 3, 4. Now, here I have 4 bowls with these ingredients. We can use these to build molecules. Let's start with epinephrine. Now, these bonds between atoms, they're made of electrons. Atoms use electrons like arms to reach out and hold their neighbors. There's 2 electrons in each bond, like a handshake. And like a handshake, these things are not permanent. They can let go of one atom and grab another. That's what we call a chemical reaction, when atoms exchange partners. And they make new molecules. The backbone of epinephrine is made mostly of carbon atoms, and that's common. Carbon is life's favorite structural building material because it makes a good number of handshakes with just the right grip strength. That's why we define organic chemistry as the study of carbon molecules. Now, if we build the smallest molecules that we can think of that follow our rules, they highlight our rules, and they have familiar names: water, ammonia, and methane, H2O and H3 and CH4. The words hydrogen, oxygen, and nitrogen, we use the same words to name these 3 molecules that have 2 atoms each. They still follow the rules because they have 1, 2, and 3 bonds between them. That's why oxygen gets called O2. I can show you combustion. Here's carbon dioxide, okay, CO2. Above it, let's place water and oxygen, and beside it, some flammable fuels. These fuels are made of just hydrogen and carbon. That's why we call them hydrocarbons. We're very creative. So when these crash into molecules of oxygen, as they do in your engine or in your barbecues, they release energy and they reassemble. And every single carbon atom ends up at the center of a CO2 molecule holding on to 2 oxygens. And all the hydrogens end up as parts of waters. And everybody follows the rules. They are not optional. And they're not optional for bigger molecules either, like these 3. This is our favorite vitamin, sitting next to our favorite drug. And morphine is one of the most important stories in medical history. It marks medicine's first real triumph over physical pain. And every molecule has a story, and they're all published. They're written by scientists, and they're read by other scientists. So we have handy representations to do this quickly on paper, and I need to teach you how to do that. So we lay epinephrine flat on a page, and then we replace all the spheres with simple letters. And then the bonds that lie in the plane of the page, they just become regular lines. And the bonds that point forward and backwards, they become little triangles, either solid or dashed to indicate depth. But we don't actually draw these carbons. We save time by just hiding them. They're represented by corners between the bonds. And we also hide every hydrogen that's bonded to a carbon. We know they are there whenever a carbon is showing us any fewer than 4 bonds. The last thing that's done is the bonds between OH and NH. We just get rid of those to make it cleaner, and that's all there is to it. Okay, this is the professional way to draw molecules. This is what you see on Wikipedia pages. It takes a little bit of practice, but I think everyone here could do it. But for today, this is epinephrine. This is also called adrenaline. They're one and the same. It's made by your adrenal glands. You have this molecule swimming through your body right now. It's a natural molecule. This EpiPen would just give you a quick quintillion more of them. We can extract epinephrine from the adrenal glands of sheep or cattle, but that's not where this stuff comes from. We make this epinephrine in a factory by stitching together smaller molecules that come mostly from petroleum. This is 100% synthetic. And that word, synthetic, makes some of us uncomfortable. It's not like the word natural, which makes us feel safe. But these 2 molecules, they cannot be distinguished. We're not talking about 2 cars that are coming off an assembly line here. A car can have a scratch on it, and you can't scratch an atom. These 2 are identical in a surreal, almost mathematical sense. At this atomic scale, math practically touches reality. And a molecule of epinephrine, it has no memory of its origin. It just is what it is. And once you have it, the words natural and synthetic, they don't matter. Maybe you guys can help me to reclaim this word, chemical, because it has been stolen from us. It doesn't mean toxic, and it doesn't mean harmful, and it doesn't mean man-made or unnatural. It just means stuff. Okay? You can't have chemical-free lump charcoal. That is ridiculous. Okay? And I'd like to do one more word. The word natural doesn't mean safe, and you all know that. Plenty of nature's chemicals are quite toxic, and others are delicious, and some are both. Toxic and delicious. The only way to tell whether something is harmful is to test it. And I don't mean you guys. Professional toxicologists. We have these people, they're well trained, and you should trust them, like I do. So nature's molecules are everywhere, including the ones that have decomposed into these black mixtures that we call petroleum. We refine these molecules. There's nothing unnatural about them. We purify them. Now, our dependence on them for energy, that means that every one of those carbons gets converted into a molecule of CO2. That's a greenhouse gas that is messing up our climate. Maybe knowing this chemistry will make that reality easier to accept for some people, I don't know. But these molecules are not just fossil fuels. They're also the cheapest available raw materials for doing something that we call synthesis, for using them like pieces of Lego. We have learned how to connect them or break them apart with great control. I've done a lot of this myself, and I still think it's amazing that it's even possible. We can make molecules that are exact copies of nature, like epinephrine, or we can make creations of our own from scratch, like these two. One of these eases the symptoms of multiple sclerosis. The other one cures a type of blood cancer that we call T-cell lymphoma. A molecule with the right size and shape, it's like a key in a lock, and when it fits, it interferes with the chemistry of a disease. That's how drugs work. Natural or synthetic, they're all just molecules that happen to fit snugly somewhere important. But nature is much better at making them than we are, so hers look more impressive than ours. Like this one. This is called vancomycin. She gave this majestic beast 2 chlorine atoms to wear like a pair of earrings. We found vancomycin in a puddle of mud in a jungle in Borneo in 1953. It's made by a bacteria. We can't synthesize this cost efficiently in a lab. It's too complicated for us, but we can harvest it from its natural source, and we do because this is one of our most powerful antibiotics. And new molecules are reported in our literature every day. We make them or we find them in every corner of this planet. And that's where drugs come from. And that's why your doctors have amazing powers to cure deadly infections and everything else. Being a physician today is like being a knight in shining armor. They fight battles with courage and composure, but also with good equipment. So let's not forget the role of the blacksmith in this picture. Because without the blacksmith, things would look a little different, wouldn't they? But this science is bigger than medicine. It is oils and solvents and flavors, and fabrics, and all plastics. The cushions that you're sitting on right now, they're all manufactured and they're mostly carbon, so that makes all of it organic chemistry. This is a rich science. I left out a lot today. Phosphorus and sulfur and the other atoms and why they all bond the way they do, and symmetry and non-bonding electrons and atoms that are charged and reactions and their mechanisms, and it goes on and on and on. And synthesis takes a long time to learn. But I didn't come here to teach you guys organic chemistry. I just wanted to show it to you. But our main goal was just to show you that organic chemistry is not something to be afraid of. It is at its core a window through which the beauty of the natural world looks richer. Thank you.